Hello, my name is Mike McGlone, and I am a NASA Curriculum Specialist with the Aerospace Education Services Project. I'd like to share the activity on landing a rover from the Summer of Innovation lesson plan on exploration. This is the first part of an activity where we build a rover and then a lander to safely land the rover on a planetary surface. In preparation for the human exploration of the solar system, NASA will continue to use remote exploration tools to gather important data for upcoming space exploration missions. In this activity, students will become involved in the engineering design process to master objectives that further illustrate remote exploration tools that NASA uses. Teams will work to design and create a model of a space exploration rover that will carry equipment and people on the surface of the Moon, Mars, or an asteroid. In the next activity, they will build a lander to safely deliver this rover to a planetary surface. After dividing your class into groups of 3 or 4 students, share with them this challenge. The team's challenge is to design and build a model of a lunar transport rover that will carry equipment and people on the surface of the Moon. Maybe your rovers will be like the Apollo lunar rover pictured here. There are always constraints on a project, from money to time, resources, and a wide range of other issues. For our rover challenge, we are asking the students to follow these constraints. Carry 1 plastic egg snugly. The egg may not be taped or glued into place. The egg represents what materials are carried in the rover. Have room for 2 plastic people. The people do not land with the rover. They will get in the rover on the Moon and drive it around. Small action figures or army men make great model astronauts. Roll on its own down a ramp with minimum rise over run of 1/3 for a distance of approximately 50 centimeters. We will talk more about rise over run in a few moments. Rover must survive the landing. This means it should be able to roll down the ramp after the landing, and the plastic egg should not have popped open. And the rover lander must be less than 300 grams in mass. This will be more important in part 2, but your rover will need to be lightweight. The basic design process is to design, build, then test your model while taking notes and data so you can analyze and redesign as needed. This chart provides a simple way of highlighting these steps for students. So the first step for the teams is to design their model. The design step is key and will require teamwork within the groups. In the end, they should be able to share at least a simple drawing of their planned rover and what materials they need for construction. The materials for this activity are easy to find. Simple cardboard from food boxes, plastic food containers, picnic supplies, and much more are available around the home or school. In fact, have students bring materials from home based on their design. Just be sure to remind them to wash any food containers. Be sure to also provide tape or glue. In addition to the supplies needed to construct the rover, teachers will need to provide a mass balance and a ramp of at least 50 centimeters to test the rovers. Ramps can be made from books, shelves, clipboards, box lids, etc. The width of your ramp will be another constraint on the rover design, so be sure to share that with your students. Now you're ready to build. While building the rover, encourage students to stick with their original plan as much as possible and wait to redesign until after testing. One of the keys to success in the design process is changing and testing only one thing at a time. Once the rovers are ready, it is time to test. To set up the test area, simply use books to elevate one end of your ramp. I've used a shelf in my example photo. Remember that the minimum slope that the rover must traverse is a rise-to-run ratio of 1:3. To determine the slope or rise-to-run ratio, measure the run or horizontal length of the ramp and the rise or vertical height of the ramp. Then use the simple equation for slope of rise over run to find the ratio. The ramp in the image has a slope ratio of 1:5. After testing at the minimum slope, students can add books to change the rise-to-run ratio. Remember to measure and calculate the slope each time. They need to discover what slope to set up the ramp to get the rover to roll easily and safely to the bottom. They also need to discover what slope is too steep for their rover. NASA is very concerned about both the safety of the rover and the safety of the people. If the slide is too steep, the rover may tumble or slide dangerously, or the impact at the bottom might jar the egg or the astronauts loose. This is a Goldilocks experiment. What slope is too much? What slope is too little? What slope is just right? After testing the rover, it is time for students to analyze the results and redesign and test as needed. After their final design is successfully tested, they can move on to Part 2 to design, build, and test the lander for their rover. I hope you and your students enjoy designing and testing your rover models. Good luck. Hello, my name is Mike McGlone, and I'm a NASA Curriculum Specialist with the Aerospace Education Services Project. I'd like to share the second part of the activity on landing a rover from the Summer of Innovation lesson plan on exploration. This is the second part of an activity where we build a rover and then a lander to safely land the rover on its surface. In part 1 of this activity, we designed and built a rover for the moon. Now we need to design a lander to take us safely to the lunar surface. Landing a rover on the moon or any planetary surface has lots of challenges. I encourage you to show your students some of the videos on entry, descent, and landing that are listed in the lesson plan. Although the astronaut team does not ride in the rover during the entry process, it must work even after a hard landing. One of the key phrases in the challenge is surface of the moon. Students will need to understand about lunar characteristics to have a successful design. For example, no parachutes or other aerobraking techniques will work because the moon has no atmosphere. So how do we design a lander to get our rover safely to the lunar surface? Well, remember our constraints. The main two we have to be concerned about here are the last two, although the rest are still important because the rover must roll down the ramp after landing to show it still works. But the rover and lander together must be less than 300 grams in mass. As mentioned in part 1, the basic design process is to design, build, and then test your model while taking notes and data so you can analyze and redesign as needed. This chart provides a simple way of highlighting these steps for students. So the first step for the teams is to design their model. The design step is key and will require teamwork within the group. In the end, they should be able to share at least a simple drawing of their planned lander and what materials they need for construction. The materials for this activity are easy to find. Simple cardboard from food boxes, plastic food containers, picnic supplies, and much more. In fact, have students bring materials from home based on their design. Just be sure to remind them to wash any food containers. Be sure to provide tape or glue. Once you've gathered your supplies, it is time to build. Remember to complete building your models before too much redesign is done. One change at a time is a key to success. Once built, remember to determine if you meet the last constraint, under 300 grams total mass of lander and rover. Now you're ready to test. Testing is simple. Just hold the lander from shoulder height about 1 meter above the ground and let it fall. Once it has fallen, check to make sure the egg representing supplies is still in good shape. Then test the rover to make sure it will still travel safely down the slope. I hope you and your students enjoy designing and testing your rover landers. Good luck.